Okay. Hi, everyone. Good afternoon, all of you. So we'll start with today's quote, and it is also Zen's quote, Zen Buddhism. So it says, life is a series of natural and spontaneous changes. Don't resist them. That only creates sorrow. Let reality be reality. Let things flow naturally forward in whatever way they like. So only thing we have to believe and understand is whatever is going to happen is for our good, and accept them as it is. And finally, everything will go to a better position. Evolution is natural, and going to good is natural. So don't resist them. That only creates sorrow if you try, because actually there is a saying that God gives you everything what you need, but not what you want. So what we want may be different and may not be met, but you will be given what you need. So that's why, so because when the wants are high than the needs, naturally we try to resist the things that naturally flow. And so we fight with nature, and it creates sorrow many times. Okay, so today is the birthday of René Laennec, and he is a French physician who invented the stethoscope. So he is the first person to invent a stethoscope. And till then, actually, people used to put their ear to listen to the heartbeat and whatever is happening inside. So, and he generally considered the father of chest medicine. And using a foot-long wooden cylinder that he placed on the chest of his patients, he was able to hear the various sounds made by the lungs and heart. For 3 years, he studied patients' chest sounds and correlated them with the diseases found in autopsy. And he made numerous other contributions to the literature of respiratory and heart disease. And he says, I had not imagined it would be necessary to give a name to such a simple device, but others thought differently. If one wants to give it a name, the most suitable would be stethoscope, he says. So he is the inventor of stethoscope. Okay, today we'll continue that problem that we have discussed in the last class a little bit, and then we'll continue with the next chapter, axial flow compressors. So before going to that, just we will recollect what we have done in the last class. That is the problem. Okay, so in the problem, so the data that we have got is, we got work input factor and the slip factor has some 1.04, sigma is 0.9, and eta C is given 0.78. Okay, and the RPM is given as 290 RPS. And the diameters are given like impeller diameter 0.5 meters, and I-tip diameter 0.3 meters, and I-hub diameter 0.15 meters. And the ambient pressure is given 1.1 bar, and temperature 295 Kelvin. Like that, these are the different data that are given. I think these are the data. I don't know whether anything, we will see. Okay, so we have found out first the work we have found out. To get the work, we got U2. This is pi d to n, and so this is I sigma U2 square. So we got this, and the power we got as m dot W. So this is kilojoule per kg, and this we got in kilowatts. Okay, and we got the pressure ratio as 1 plus eta CW by Cp T01 to the power of gamma A by gamma A minus 1. So this is the way we got the pressure ratio. And W is also equal to Cp into T03 minus T01 which gives me T03 in Kelvin. And T03 is equal to T02. So T02 I will get. And R is equal to P03 by P01. So this gives me P03. Okay, so these are things we found out. And then we are asked to find out what is the inlet angle. Okay, so for that we have taken the inlet triangle at hub, mean, and tip. Okay, so we got this as CA and this as UI hub, UI mean, and this is UI tip. So this is V1 tip, this is V1 mean, this is V1H, and this is beta 1 tip, beta 1 H mean, and this is beta 1 H. So we are asked to find out that. So we have to find out CA. So we know that m dot is equal to rho 1 A1 CA1, and A1 is equal to pi by 4 DET square minus DEH square. So we got this. So we have to get, because rho 1 and CA1 both are unknowns, so we have to assume one of them and get the other one. Right? As I told, CA is normally around 150 meter per second. So we can start with that. And if you start with CA, so rho 1 is equal to m dot by A1 CA1. So this gives rho 1. Okay, CA1 is C1 also. So T1 is equal to, okay, we will not do that first. So T1 is equal to T01 minus C1 square by 2Cp, and P1 is equal to P01 into T1 by T01 to the power of gamma A by gamma A minus 1, and rho 1 is equal to P1 by T1. So CA1, now this is updated. M dot by rho 1 A1. So like that we will get, and these things are repeated. Okay, sorry, up to here. Till convergence. So this will give you CA, and once you get CA, and so UET, this is pi DET by pi DETN, this is pi DEM, and this is pi DEH M. Okay, so U I got, CA I got, so beta 1 is equal to this is beta, so opposite side by adjacent side, so tan inverse CA by U. Okay, so if you put I hub speed here, you will get beta 1H like that, beta 1M, beta 1T, all these things can be found out. And then we also checked about the Mach number here. So V1 T is equal to root of CA square plus UET square. And so M V1T is equal to V1T by root gamma or T1. So this gives me the Mach number at the I tip. So this is for check whether we need IGV or not. Okay, so this is the way we have done at the inlet. Now coming to the exit, you are asked to find out what is B2. So we know that A2 is equal to pi D2 B2, and so B2 is to be found out. So I have to find out A2. So m dot is equal to rho 2 A2 CR2. So here rho T is to found out or CR2 is to found out. So first assumption we have made is, what is the assumption we have made? Anybody remember?
CR2 is equal to C2.
CR2 is equal to C1. So I'll get, say, CR2 is obtained. So rho 2 is to be obtained. For rho 2, P2 and T2 are to be obtained. So we have got CR2 and CW2 is equal to sigma U2. So C2 is equal to root of CR2 square plus CW2 square. C2 I got. And so I can get T2 is equal to T02 minus C2 squared by 2CP. So we get T2. To get P2, first I have to get P02. So for that, what we have assumed is, what is the second assumption?
So losses are equally divided between
Losses are equally divided between impeller and diffuser. So eta C is given. So find out eta impeller. So once I get that, then P02 by P01 is equal to 1 plus eta C, eta impeller W by CPT01 to the power of gamma A by gamma A minus. So this gives me P02. So once you get P02, P2 by P02 is equal to T2 by T02 to the power of gamma A by gamma A minus 1. This gives me P2. So P2 and T2 are obtained. So rho 2 is equal to P2 by RT. So m dot R is equal to rho 2 A2 CR2. See, rho 2 is known, CR2 is known. So A2 is equal to m dot by rho 2 CR2. So A2 is equal to pi D2 B2. So which gives me B2 is equal to A2 by pi D2. Okay, this is the way we got the width of the impeller channel at the exit. And next, coming to diffuser vane. So between impeller exit and diffuser vane, we have vaneless space. So what is in vaneless space, how the behavior will be? RCW is equal to constant. This is actually called as free vortex, or angular momentum is equal to constant. Okay, this is the way we assume. So if you know the vaneless space, width of vaneless space, so diameter at diffuser inlet is equal to impeller diameter plus 2 into vaneless space. So this gives the diameter of the diffuser inlet. Actually, we got this as 0.5 meters, and this is given as 0.05 meters. So it will come to be 0.1. Okay, 0.1 meters, so 0.6 meters. Okay, this is the way the diameter is obtained. And now we can get actually CW, because RCW at impeller exit is equal to RCW at diffuser inlet. So this gives me CW at diffuser inlet. So here also it is put like 2, CW2 at diffuser inlet. And so CR2 is to be assumed. Okay, so it should be diffusing. So actually we got CR2 or CA1 as 143 meter per second. So here the CR2 should be less than that. So we'll take approximately some 100 meter per second like this. And for the first assumption, we have taken CA1 as 150 meter per second because it is around this value it will be. But here at the diffuser vane, we will take 100 meter per second as the assumption. So once you have CR2 and CW2, the same procedure we will put. C2 is equal to CR2 square plus CW2 square. So T02 and T02 will be same. Whatever is the impeller exit, the same values will be there at the diffuser inlet because there will not be, assuming there are no losses. Okay, so this is by assuming no losses, and T02 is constant because Q equal to 0, W equal to 0. So T2 is equal to T02 minus C2 square by 2Cp, and T2 is equal to T02 into T2 by T0 to the power of gamma A by gamma A minus 1, and rho 2 is equal to P2 by RT2. Okay, so CR2 we want, right? So A2 is equal to pi D2 D2. Here D2 I have to put the diffuser vane diameter, so 0.6 meters. Like that. So here I'm going to get CR2 is equal to m dot by rho 2 A2. So again, just check the value because CR2 is assumed, and you repeat this till you get CR2 same. So once you get CR2, angle at diffuser inlet. So it is something like this. So this is CW1 and this is CW2, CR2, and this is C2. So this is alpha 2. So this is the angle of the at which it enters the diffuser, right? Here for rotor or the impeller, the angle should be equal to relative velocity. But here there is nothing like relative velocity. So the angle of the diffuser vane should be equal to the angle of the absolute velocity that is coming to the diffuser. So tan alpha 2 is equal to CR2 by CW2. So which gives me alpha 2. This is the diffuser angle at the inlet of the diffuser. Then it is asked about the throat. So here, if these are the diffuser vanes. So somewhere there will be throat. So this is the diameter at which the throat happens to be. Okay, so here. Okay, these are the things last class we have done, and these are the things. This is the depth. So number of diffuser vanes is given to be 12. Okay, we have done at till this point. Okay, tan inverse CR2 by CW2 is this. Okay, now again we have to do the same thing. So the throat width of the diffuser channel may be found by similar calculation. For the flow, we assume to be throat radius is 0.33 meters. Right, so throat radius Actually, diffuser inlet is 0.3 meters, diffuser radius. And the radius at the throat, because if you add this width to the throat, it is given to be 0.33 meters. Okay, so at the throat. So again, the same thing is to be used to get CW2, right? Because R2CW2 is equal to R2CW2 at the diffuser inlet and the diffuser throat. So we can get CW2 by RCW is equal to constant. Again, assume CR2. And same things, because T02 and P02 will not change. So first you calculate C2, and then T2 is equal to T02 minus C2 square by 2Cp. And P2 is equal to P02 into T2 by T02 to the power of gamma A by gamma A minus 1. Rho 2 is equal to P2 by RT2. And A2 is equal to, again, pi D2 B2. So this D2 I have to take as 0.66 meters. Right? So then m dot is equal to, sorry, CR2 is equal to m dot by rho 2 A2. So get CR2 and repeat these calculations, right, till you get CR2 converged. So that is the way first I have to do. So try CR2 83 meter per second. You can even start with 90 or something, because previously how much we got 97.9 as the CR2. So it will be still less than that. So you can try with 90 or 85 or something. So it will come to okay, 83 you start, it started, the same calculations are repeated, and so it is found to be 83.3. This gives the direction of flow to be 15 degrees. Okay, so once you get it to 15 degrees and the area here, because the angle is alpha 2, which is tan inverse CR2 by CW2, I have to take the area normal to that. So I have to multiply to this A2 by sine 15. A2 at the throat is equal to A2 into, it is found to be 15 degrees there. So sine 15 degrees, or alpha 2, you can say. So that is the way you have to find out what is the area at the throat. And this area, okay, this is 0.0365, that is 2 pi into 0.33 into this. This is 0.0365 into sine 15, and this is the area. This is the area at the throat. I have 12 diffuser veins. So the total area is that much. So for each throat, there are 12 throats will be there. So for each throat, it will be this divided by 12. And so if you want throat width, so this is the depth of the impeller channel, 0.0176, which we calculated at the beginning. Actually, if this is the volute, if this is the volute, this is the width. Okay, that B2. Okay, so that will be same, right? Either impeller exit or diffuser inlet, or at the throat, the depth of the thing will be same. So this area by 12 into the depth gives me the throat width. Okay, so this is the way I have to calculate. Okay, this completes the problem. But usually, if you check all the exercise problems, the diffuser calculation will not be included, because the length of the problem will become more. But you have to know how to do it. Okay. And coming to the volute casing, because we have seen how it behaves in veinless impeller, veinless space, and then diffuser veins, and then we have volute casing. And volute casing, right, it will be, the volute cross section will be of different types. You can have circular cross section, or trapezoidal cross section, or rectangular cross section, like this. Okay, so here this is very easy because it will be like two plates. The impeller will be there, this side one plate, this side one plate will be kept, and this spiral thing you have to design. Okay, that is the way it will be. This is rectangular channel. The manufacturing is very easy, and this is normally preferred in blowers. And this is circular one. Even for pumps also, you will see, if you see in your house or somewhere, the centrifugal pumps and all, you will see circular one as the volute. Or even compressors also, we use circular volute. Okay, so these are, and trapezoid also you can try, but usually this is not much preferred. Usually we either use rectangular or circular, but trapezoidal also can be experimented. So circular volute usually preferred for compressors and rectangular for blowers. Okay, so these are the things. Okay, as I told, some additional notes is if there is IGV. If there is IGV, there will be pre-Birla and CW1 not equal to 0. So W will be U2 CW2 minus U1 CW1. Okay, and also inlet triangle, now it is not like this. This will be like this. And this is angle of pre-Birla. Okay, and this is CA, which is the flow component. And this is U. And this is V1. Okay, so you have to calculate all the things according to this. Okay, maybe I think in Ganeshan there may be one or two problems, or even in the exercises also, just to check it. So this is one of the things you have to remember. And another thing, sometimes it may be aircraft application. So it may be flying at some altitude h and with some velocity. I will put the aircraft. Okay, so aircraft velocity is given. And so at h, I will get P1 and T1 from atmospheric tables. Okay, so what is this P1, T1 now? Previously, whatever ambient conditions are given, they are taken to be P01 and T01 because the compressor is stationary and all the air is stationary. But now it is not like that. The compressor is moving, that the aircraft is moving. So the conditions at compressor inlet, because here it will be something like this. So at this point, I want conditions. Here, P1, T1 is given. And so air is coming with aircraft velocity. Air is entering with that. So I have to get T01, T01 based on this velocity. So T01 is equal to C1 square plus, sorry, T1 plus C aircraft square by 2CP. And P1 by P01. P01 is equal to P1 into T01 by T1 to the power of gamma A by gamma A minus. So these are the conditions at the compressor inlet. And now you have to kind of find out the static conditions. So you have to understand between the static conditions here and the static conditions here. This is aircraft velocity it is entering, but here the velocity may be different because of the diffuser. So here I have to find out CA. This CA is different, CA aircraft is different. So this I have to find out by iteration. Is that clear or not? Whatever problem we have done now will be from this point onwards after getting this P01, T01. So in the first problem, we are given P01, T01. Now we have to calculate P01, T01 from here. And after this, we have to get the static conditions here. Assuming CA. Is it clear or not?
Yes, sir.
Yes, sir.
So yeah, this will be given, I think, in your exercise problem in the Cohen and Rogers, Saran Muthu. The second problem, I think it is given like this. So you have to do according to this. Because usually, whenever I give that problem, people get confused and say, sir, because you told ambient conditions or stagnation conditions, I have done like that. But it is moving, right? So ambient conditions are not now stagnation conditions. I have to use this aircraft velocity to get the stagnation conditions at the compressor inlet. Okay, so this is the way we have to do the problem. Okay, as I told, you have to try problems of centrifugal compressor. There will be one problem on that also in the mid-exam. Okay, this is about, I will stop centrifugal compressors here. So we will do the axial compressors. Okay, so already we have discussed many features of axial compressors. And so again, if you compare it to centrifugal compressor, so what are the things? We have high mass flow, low pressure ratio per stage, right? And easy for multi-staging, right? Can have any overall pressure ratio. Because it can be multi-staged, though the pressure ratio per stage is less, I can have any number of stages and I can have any large amount of pressure ratio. Okay, and low frontal area and high efficiency, but narrow range of mass flow compared to that. And yeah, I think these are the main characteristics of this compared to the centrifugal compressor. So preferred in aircraft applications and complex in designing and expensive in manufacturing and mainly cannot be used in contaminated atmospheres. Right, so if anything mud-like thing, if it gets stuck to the blade, okay, so what happens? Its profile changes, its performance changes, so everything gets degraded. So you should have clean atmosphere. Clean environment. Okay, so these are the various characteristics of axial compressors. Then so here a stage is equal to again a rotor and stator. So again, the same things, whatever we have discussed. So here W is negative. So work is given. Because work is given, T naught increase and P naught increase. Right? And because work is positive, negative, or work is given, the absolute kinetic energy increase. Right? Due to given work. Okay, so here H naught increase. So because kinetic energy increase, and also because this is a diffusing process. So because diffusing process, there will be decrease in the relative velocity, increase in the pressure, increase in the density, increase in the temperature, because it is a diffusing process. Okay, and so these are the things happen. And coming to stator T naught is equal to constant, and P naught also equal to constant if no losses. Otherwise, P naught decrease, entropy increase if there are losses. So this is also diffusing process, means velocity decrease. Here absolute velocity only, there is nothing like relative velocity. Here absolute velocity is increasing in the rotor, so it will come with high kinetic energy for the stator. So that kinetic energy, I want to convert it to the pressure energy. That's why C decrease. And because C decrease, P increase, rho increase, T increase. Okay, so this is the way the properties change across rotor and stator. Enthalpy also increase. Okay, and so here I'll put this state as 1 here and 2 here and 3 here. And again, the same way, and W is equal to Cp into T naught 3 minus T naught 1, and T naught 2 equal to T naught 3 in the diffuser. So this is also is Cp into T naught 2 minus T naught. And the power is equal to m dot W, same. And R also same, R is equal to 1 plus eta C W Cp T naught 1 gamma A by gamma A minus 1. These are also same. And W from Euler's equation is equal to U into CW2 minus CW1. I am not writing CW1 minus CW2 because W is negative, right? So, and C is increasing. So CW2 is greater than CW1. Or C2 is greater than C1. There will be increase in the kinetic energy. I know CWT is more. Okay, so that's why I'm putting CW. This is only quantity. If I put CW1 minus CW2, it will become negative because work is negative. But if I want quantity, I'm just putting U into CW2 minus CW1. Okay, so these are the formulae which we have already derived. Okay, so now we will see how the velocity triangles will be. Okay, so again, these are simple. And one more thing which I wanted to discuss in centrifugal compressors is so as I told in general, so I told velocity triangles are acute for compressors and obtuse for turbines. So just if you recollect what type of triangles we have used at the inlet and exit, you can check that we have acute triangles only. For forward wind compressor, you will get obtuse, but as I told that we don't use. Okay, that's why it is out of this thing. And even for radial compressor, where I will have right angle triangle, there because of the slip, it becomes acute triangle only. Okay. So, and the inlet, if the IGV is not there, then it is right angle triangle. But if IGV is there, again, that also become acute triangle. So both at the inlet and exit, you are going to have acute triangle or right angle triangle, but never obtuse triangle. So this you remember. So whatever statement I have given, you can check it, right? Is it clear what I'm telling?
Yes, sir.
So all the concepts must be clear. So it is not the question of marks. Okay, so if you go on solving some problems, or if you just remember and note down the things and all, you can get good marks. But you have to understand the concept, right? So when you attempt Viva or something like that, so you should be easy and feel comfortable and confidence. Okay, that is important. Okay, now if I draw axial compressor cascade. Okay. I have to draw the blade. Again, as I told you, have to be careful when you draw the cascade. Okay. You see that it comes in this line like this. Okay. And so here, if I take the mean line, so this gives the direction for the inlet velocity V1. And it has to come with like this. So this gives the exit velocity direction V2. And here, two main things you have to remember. So for the axial compressor cascade, U1 equal to U2 equal to U, because it enters and leaves at the same radius. R1 equal to R2 equal to R. Okay, the blade speed is same at the inlet and exit. This is one of the main thing. The another thing is, because m dot is rho 1, A1, CA1. Okay, and the compressor usually will be converging like this from inlet to exit. So we are drawing like that only, isn't it? So, and because from inlet to exit, rho increase. Okay, rho ACA I will write like this. Okay, rho ACA. So if this is the inlet and this is the exit, so inlet to exit, there will be increase in the density because pressure is increasing, density increase, but area is decreasing. So we will design in such a way that CA remains constant. Because rho is increasing, A is decreasing, that compensates each other, and CA remains constant. So CA1 equal to CA2 equal to CA. This is the second one. Okay, for all velocity triangles, the base of the triangle will be same at the inlet and exit. And the height of the triangle also will same at the inlet and exit. Okay, that is an easy thing, and it will be easy to draw also. Is it clear what I am telling? Okay, and then we have got V plus U equal to C, right? So V already I got, I have to add to it U. I have to add in such a way that I get acute triangle. I get like this. And this is U. And this is C1. And here also I have to add that way. And U length should be same. So it will become like this. This is C2. And this is U. So cascade is moving in this direction. U. This is inlet triangle. Is the inlet triangle clear or not? And so you can see the conformation. So C will be increasing because work is given, absolute kinetic energy increase. C1 should be small, C2 would be large. C2 is greater than C1. And because it's diffusing process, V should decrease relative to blade, because relative to blade, it should diffuse. So V should decrease. So V2 should be less than V1. So that is to be confirmed from these triangles. Is that clear?
Yes, sir.
And so the height of the triangle, this is CA1, CA, because both are same. CA. U is same, CA is same. Okay. And so these are tangential components, CW1, sorry, VW1. This is CW1, sorry, 2. VW2, CW. These are exit triangles. And so at the inlet, this is VW1. This is CW1. Okay, these triangles, if you draw, now whatever relations I write, you will understand. Okay. Okay, I will draw this. Okay, so these are the triangles. And another thing is, we show the direction, the angles with respect to axial direction. And this is axial direction. Okay. And these angles, relative velocity angles are beta, absolute velocity angles are alpha. Relative velocity angles beta, absolute velocity angles alpha. Okay, alpha 1, alpha 2, beta 1, beta 2. Okay, now I will write some relations. If there is any problem, you ask me, right? And so from the first triangle, U equal to VW1 plus CW1. And from the second triangle, U is VW2 plus CW2. So which actually indicates CW2 minus CW1 equal to VW1 minus VW2. Okay, and another thing is CW1 is CA tan alpha 1 and CW2 is CA tan alpha 2 and VW1 is CA tan beta 1 and VW2 is equal to CA tan beta 2. Okay. So from here, I will get, this is CA into tan alpha 2 minus tan alpha 1. This is CA into tan beta 1 minus tan beta 2. Okay, if I take out this, the angles are related like this. Okay, and now I will come to W. W is equal to U into CW2 minus CW1. And we have seen that I can write in terms of VW1 minus VW2. Because why I write like this is blade angles are fixed. Okay, so I try to express in terms of blade angles. So this is equal to U, and VW1 minus VW2, I write it as CA tan beta 1 minus CA tan beta 2. So this is the expression for work. You have to remember that. Okay, and this both sides I divide by U square. So W by U square is equal to 1 U gets cancelled. So CA by U into tan beta 1 minus tan beta 2. And W by U square, it is non-dimensional work. This is given as work coefficient, and CA by U is non-dimensional flow. So this is flow coefficient. So I will write this as psi equal to phi into tan beta 1 minus tan beta 2. Okay, these are work coefficient, and this is flow coefficient. Okay, so this is one important expression. Okay, and then another thing is so this is actually rotor, and if I have a stator after this, stator also diffusing process only like this. So it enters C2 with alpha 2 enters here, and it also comes with less C3 and alpha 3. So it comes something like this, C3 and alpha 3. So if I design in such a way that if C1 equal to C3 and alpha 1 equal to alpha 3, if there is a next stage, so this will become C1 and alpha 1 for the next stage. Okay, so whatever is coming out here, it enters the next rotor. So if C1 equal to C3 and alpha 1 equal to alpha 3, I can have the same triangles for the next stage also. So this is called as repeating stage. What is the advantage of repeating stage? Same rotor blades and stator blades can be used for the next stage and next stage like that. Okay, so if C1 equal to C3, alpha 1 equal to alpha 3, it is called as repeating stage. If C1 equal to C3 and alpha 1 equal to alpha 3, H03 minus H01 is equal to, or okay, I will write T03 minus T03 minus T01 is equal to T3 minus T1. That is DH0 is equal to DH, because D of KE is 0. Is it clear? So here we define what is called as reaction. Reaction is delta H across rotor by delta H across stage. And delta H across rotor is H2 minus H1. Delta across H across stage is H3 minus H1. And if I have repeating stage, H2 minus H1 by, I can write H03 minus H01, which is W, the total work. So this is delta H across rotor. So relative to blade, right? H naught is constant. If I take absolute way outside, so there is some work is given, H naught increase. But relative to blade, H naught will be constant. So H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. And H2 minus H1 is equal to V1 square minus V2 square by 2. And if I see the velocity triangles, what is V1 in terms of CA? V1 is this is CA, right? So V1 by CA is in terms of beta 1, which will come sine, cos, secant, cosecant, tan, B, cot or something. V1 by CA. Diagonal by adjacent side. What is that?
Cot, sir.
Is it cot? No. Adjacent by opposite is cot.
Secant.
Secant, yes. So this will be CA square secant square beta 1 minus CA square secant square beta 2. That. And CA square into secant square beta 1 minus secant square beta 2. And how can I write in terms of tans? Secant square is
1 plus tan square.
1 plus tan square beta 1. This is 1 plus tan square beta 2. 1 gets cancelled. So I will get tan square beta 1 minus tan square beta 2. Okay. And now the reaction is H2 minus H1 by the work. That's what we had done in the previous one. Okay. H2 minus H1 by work. So H2 minus H1 is this we have written CA square into tan square beta 1 minus tan square beta 2. And by W is UCA into tan beta 1, tan beta 2 minus tan beta 1. So if you just see back, so W is equal to UCA into tan beta 1 minus tan beta 2. Okay, tan beta 1 minus tan beta 2. So now one CA gets cancelled. So I will get CA by U. Here if I write it as tan beta 1 plus tan beta 2 into tan beta 1 minus tan beta 2, I am going to get tan beta 1 plus tan beta 2. This is R reaction. Okay. So R is equal to phi tan beta 1 plus tan beta 2. Okay, this is important. Okay, so this is second relation. Previously we got psi is equal to phi into tan beta 1 minus tan beta 2. And we got R is equal to, I think on 2 is missing, I think. Here, yeah, here 2 will be there, right? So here 2 will be there. By 2, okay. Yeah. By 2, like this. It will be like this. So R is equal to phi by 2 into tan beta 1 plus tan beta 2. So this R, phi and psi are design parameters. So for any design, if you know R, phi and psi, from the first equation you can get tan beta 1 minus tan beta 2. From the second equation you can get tan beta 1 plus tan beta 2. And by solving the above equations, for a given R, phi, and psi, we can solve beta 1 and beta 2, right? And usually u is equal to pi dn by 60. Okay, so this will be known to you. And so u is equal to, okay, I can say, so once beta 1 and beta 2 are known, u is equal to Ca into okay, Ca can be obtained from inlet conditions. Okay, so if u and Ca are known, so u is equal to Ca into tan alpha 1 plus tan beta 1, and also equal to tan alpha 2 plus tan beta 2. Okay, so actually here also, if u is known, because phi is equal to Ca by u, so you can get Ca from here. And once you know Ca, then you can get, in the first equation, it will give you alpha 1, and second equation will give you alpha 2. So once you know these alpha 1, alpha 2, beta 1, beta 2, and u, Ca, so everything you can get, all the components, Cw1 is Ca tan alpha 1, and Cw2 is equal to Ca tan alpha 2, Bw1 is Ca tan beta 1, like that. All the things you can find out. Okay, this is the way we can solve all the velocities, angles, and everything. And one more thing we like to discuss is R is equal to Ca by 2u tan beta 1 plus tan beta 2. And this is also can be written as 2u. And Ca tan beta 2 is Cw1, Bw1. This is Bw1 and this is Bw2. And sometimes we can write this as u minus Cw1 plus u minus Cw2 from the exit triangle. So 1 by 2u into 2u minus of Cw1 plus Cw2, or, and this also can be written as Vw1 plus Vw2 by 2. This is 1 minus Cw1 plus Cw2 by 2. So there are different ways of writing. This is one way you can write, and this is one way you can write in terms of Vw1, Vw2, and here in terms of Cw1 and Cw2. Okay, and now what I want to discuss is what happens when r equal to 0, r equal to 1, like that. Okay. So when r equal to 0, r equal to 0 means, so tan beta 1 plus tan beta 2 equal to 0. We'll get here. So actually this will give you beta 1 equal to minus beta 2. So here we are going to get symmetric blades. So here it will be something like. So it comes like this, it goes like this. So this will be beta 1. And so here, if V2 is going like this will be beta 2. And beta 1 will be equal to -2. Exactly the same angle it is coming out, but it is going in the opposite direction. It is coming like this and it is going like this. So beta 1 equal to minus beta 2. So I will have what are called as symmetric blades. And also R equal to 0 means H1 equal to H2. Okay. And V1 equal to V2. No change in enthalpy, no change in relative velocity, and no diffusion. Okay. Because the area that is coming out here and here will be same. There is no change. Okay, so we don't use it, but I'm telling like impulse turbine, it is like impulse compressor type. So there will not be any diffusion. R equal to 0 means across rotor, there is no diffusion. All the diffusion will take place in the stator only. Am I right? Because R is equal to H2 delta H of rotor by delta H of stays. So what I am telling is delta H of rotor is 0. So whatever delta H across rotor is stays means delta H rotor plus delta H stator. Okay, if delta H rotor is 0, the complete thing is taking place in the stator only.
Sir, then there won't be any pressure change, right, sir?
Yeah, there is no pressure change. Okay, so V1 equal to V2, P1 equal to P2. There is no diffusion. Okay, we don't use them, but I am telling reaction 0 means this is what happens. You are getting symmetric blades. Okay, so beta 1 equal to minus beta 2. If I have R equal to 1, so the other formula we have got is CA by 2U into 1 minus, sorry. So this formula if I take, so CW1 R equal to 1 means this is 0. So CW1 equal to minus CW2 or alpha 1 equal to minus alpha. That is C1 equal to C2 minus C2 or C1 equal to C2. That is across, okay, I can say in that way, what is it? Okay, here one more thing I want to say. So here, it is entering stator inlet is C3 alpha 3, which is equal to C1 alpha 1. And stator exit, what are stator exit conditions? So this stator exit, from the stator exit, it has to enter, sorry. What is stator? This is stator exit. This is stator exit. C1 alpha 1 are the stator exit. What is stator inlet? This is coming as the stator inlet. Am I right? This is entering the stator. This C2 is entering the stator. So stator inlet is C2 alpha 2. C2 alpha 2 are stator inlet. C1 alpha 1 are stator exit. Okay. So here, when I am coming to this, alpha 1 equal to minus alpha 2 means C1 equal to C2 means there will be symmetric blades for stator. So there is no diffusion in the stator. So because R equal to 1 means delta H across rotor by delta H across stays is equal to 1 means delta H across stator is 0. So across stator for R equal to 1, stator blades are symmetric. So C is constant and P is constant across and H is constant across stator. So all the diffusion in rotor only. That is pure reaction. This is pure reaction type. Okay, like this. So remember, if complete diffusion takes place in the stator and no diffusion in the rotor, that is impulse type. If complete diffusion in the rotor and there is no diffusion in the stator, that is reaction type, pure reaction. So no diffusion means no change in the velocity, no change in the pressure, no change in the enthalpy across that particular blade, and it is symmetric blade. Okay, this you have to understand with logic. Okay, so finally, I just talk about this. R is equal to 0.5 means 50% reaction. So R is equal to, we got Ca by 2U tan beta 1 plus tan beta 2. So this is 0.5 means 1 by 2. Okay, so if 2 gets cancelled, so Ca into tan beta 1 plus tan beta 2 is equal to U. Okay, this is what we got. But if you remember the first initial relations, okay, U is equal to Ca tan alpha 2 minus tan alpha 1, Ca into tan beta 1 minus tan, sorry. Yeah. Okay, we have got U is equal to Cw1 plus Vw1, which is equal to Ca into tan alpha 1 plus tan beta 1. And also we got U is equal to Cw2 plus Vw2, which is Ca into tan alpha 2 plus tan beta 2. Okay, these are for any cascade, these are relations. But this is relation for 50% reaction. Okay, so if you take this and this, so what is that I can conclude? This is equal to this means.
Alpha 1 is equal to beta 1.
Alpha 1 equal to beta 2.
Alpha 1 is equal to
Beta 2. And if I
beta 2
compare this and this,
Beta 1
alpha 2 is equal to beta 1.
alpha 2 equal to beta 1. Okay, so this is we consider. Okay, maybe we will continue in the next class. It is already, we have gone beyond. So we will continue this in the next class. You remember this result. Okay, so we will see what is the specific specialty of 50% reaction in the next class. Any questions till now? So you go through all the relations. You should not get confused. Okay, so you should be comfortable and confident about the relations. Any questions?
No, sir.
Okay. So we'll quickly go through a story. So these are the figures. So this is a converging like thing, right? So the area of the blade or the height of the blade decreases. There are various types of design. So the top may decrease like this, or the bottom one may increase, or both may happen like that. But the area of the flow gradually they decrease here till here. And these are the cascade. This is turbine cascade and this is compressor cascade. You can see the area is increasing in the compressor. In the turbine, the area is more here and less here, it is decreasing. And this is the thing already we have discussed for centrifugal compressor. These are the velocity triangles. Okay, this we will discuss next class. Okay, it is maybe it will take 5 more minutes. It is Honda story. It is also inspiring story. So I always tell about the people who from rags to riches, like a very poor family to a highly successful thing. And born to a blacksmith and a weaver, Honda had an innate passion for machinery. The story of him chasing a car that passed by the town when he was very little has been a topic of many of his interviews. So when he has seen a car, he was so much thrilled, and that became the passion. He said that the smell of oil was he could not forget, and the thrill is unimaginable. As he was growing up, his father's bicycle repair shop enriched Soichiro's interest in the craft and enhanced his tinkering capabilities. His devotion to technology was only empowered by the country's sudden shift from agriculture to that of manufacturing during this time. And he grew up puzzled by the world's development and found his own way to understand it. At 16, his knowledge of machines and his dexterity in handling them were beyond his years. School no longer appealed to him. He wanted practical education. He opted to halt formal training and rather apply as an apprentice in one of Tokyo's automobile servicing companies. And he worked as a mechanic apprentice for Art Shokai, that company in Tokyo. The company serviced cars needing repair and maintenance. It was a difficult time for him. However, an apprentice were not paid wages. They were just given a bed to sleep and food to eat, nothing more. This did not deter his yearning to learn, though. He closely studied each vehicle rendered to his care. He was very competent in maintenance and repair. He was able to devise ways to simplify elaborate repair procedures and shared this with his co-workers, making their jobs easier. Later, he developed a flair for invention. He used automotive tools and parts in an uncanny manner. He was as creative as he was analytical. He was also just a young boy. He spent his spare time reading motorcycling magazines and committing a memory of each detailed description he read. He also closely followed international motorcycle racing. Not long after beginning the apprenticeship, he actually seemed educated in the field. His efforts were rewarded as the Art Showcase management took notice of his capabilities. The owner then took it upon himself to teach him everything else he knew about the trade, not only about machinery, but mostly about the business. He was also a very valuable asset to the company, used his abilities when they ventured into manufacturing cars. And he was able to produce quality spare parts from unconventional sources and through unorthodox means. Thereafter, he rise through the ranks his rise through the ranks was unstoppable. As he ventured into racing, he was named accompanying engineer, and later he was given full independence to manage the branches near his home. He was only 22 at the time and became very successful. He became the most sought after mechanic in the region. And his involvement with Art Shokai ended when he intended to expand the company's undertakings into manufacturing. He wanted to manufacture piston rings, but the management saw no benefits in the venture and shot his idea down. He left it. To pursue his dream, he left Art Shokai and started his own business in manufacturing piston rings. But everything will not go smooth. Due to the complexity of the material, he has to go back to school to have in-depth knowledge of the metals. After long days of making pistons, see, he has studied after that because of his particular passion. So he has chosen what he has to study. So making piston rings and long nights of studying and a lot of adjustments in between, and he seemed to have achieved his dream. Okay, so though he got piston rings, now what happened? Soon thereafter, his rise through the ranks was sorry. He was finally able to make quality piston rings and supply Japan's automotive giants, including Toyota. He was on a roll with his manufacturing business until the war broke out. The company was taken over, and his position as president was reduced to that of an operation manager. Most of the male employees were drafted into the military, which left him with women in his rank and file. He made certain adjustments in the manufacturing process, making it easier for the women to comprehend and perform the tasks. The company functioned smoothly nonetheless until his building containing the piston rings and all his machinery was destroyed during the bombing raid by American warplanes. So his industry also got destroyed. And he lost most of his investments. The few he salvaged after the war, he sold to Japan's big companies to be able to get back on his feet. The broken country did not break his love for the automotive industry, however, nor did it break his spirit. From the rubble created by the war and the country's need for practical motor vehicles rose the Honda Motor Company, and he pursued his dreams of manufacturing motorcycles. The first Honda motorcycle, literally an engine connected to a bicycle, was made in 1948. Further developments created useful and efficient machinery that created to the people's needs. And within a decade, Americans had embraced the idea of Honda motorcycles, and shortly after, his creations were winning international motorcycle races. And his automotive line was not as widely accepted as his motorcycles were. The Department of Trade at the time discouraged him from getting into car manufacturing because many had done also and they were already quite successful at it. There was no place for another startup company crowding the market. But still, he continued working on his prototype and created a small yet efficient and sturdy model fit for the times. He was given permission to proceed and build a competitive empire, and he did. And he said success can only be achieved through repeated failure and introspection. Okay, this is important. When you failed, you have to introspect and find out where he has failed and why he has failed. So his journey was long and difficult, his life full of trials and challenges. Several times he was shot down, and several times he stood up to continue what he loved doing. At no point did failure prevent him from pursuing his dream. Failure only urged him to find a way to do so and heightened his need for learning. He used his love for automotives, his knowledge and skills to pursue his dream, and despite the obstacles, he fought within reason to achieve his dreams. And today, Honda Motor Company manufactures motorcycles, cars, and even marine and aerospace parts and equipment. And his innate characteristics were embedded in his company. Being creative and giving the consumers what they need sets the company apart. So also creating a machine and studying it and find ways to make it better was a virtue he passed on. And most importantly, having the patience to see each task through was necessary. Honda is now one of the leading automotive manufacturers, and the company's motorcycles are still winning races around the world. And he enjoyed the benefits of his hard work and diligence until his death at age 84 in August 1991. Okay, that is it. And he says, instead of being afraid of the challenge and failure, be afraid of avoiding the challenge and doing nothing. And he gives another important point for the management. If you hire only those people you understand, the company will never get people better than you are. Always remember that you often find outstanding people among those you don't particularly like. Okay, so it's one management secret, he says. So always people take the people whom they like, but it is not that. There will be people who are very creative in the people whom you don't like. Okay, thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.